Okay, I believe we are recording. Welcome back to Pock Racers for this winter quarter. Um, Happy to see you guys again. I hope, I hope you guys have been managing with the fires and all the adjustments being made. Yeah, so today's lecture four, we'll be getting into backpropagation and neural networks. Some quick announcements before we really get into it. Um, yeah, lab two, we're gonna have a hard deadline this Sunday. So that's in 2 days. I hope most of you guys are finishing it up by now. And yeah, just reach out to me if you guys need any help. So for lab three, which should be posted tonight as well. I'm not sure if it'll be at the same time or what time it'll be for compared to this lecture, but it'll be dropped today on Friday. Um, it's definitely more of a hardware focused lab, so you will only be needing to come into the IEEE lab as opposed to like lab two, which was all online. But lab three is hardware focused. We'll be actually building the racers, so look forward to that. It'll be fun. Um, the thing about lab three is that we will be needing to do soldering, so there should be a tutorial within lab three, but it is helpful to see physically in front of you how to do it and how to set up the lab and everything. So, um, it'll be helpful if you could come in during a time when I'm there, or most of the IEEE officers, if not all of them, should be able to help you as well. So come into the lab and ask them how do you solder, and they should be able to help you out. We will be having a work session. I haven't set a date yet, probably either this week or next week. I'll send out an announcement about that soon. So besides that, we can go ahead and get started with the lecture. So yeah, let's do that. Quick little plug. We're gonna be running through some of the stuff in C147 neural networks and deep learning with Jonathan Cow, great teacher. So if you're interested in this stuff and want to learn about more, I recommend taking that class. So here we go, neural networks. So what are neural networks? Neural networks are basically our way of trying to copy the model of the brain. So the brain is made up of many neurons, and these neurons are like a unit, and they're like pretty identical within the brain, and there's made of so many of them. So how the brain is actually able to process things and learn is through the connections and the structure of these neurons. So the goal of our artificial neural networks is to copy this format and to hopefully be able to learn. And in our case, neural networks, each neuron is going to be a logistic regression model. And looking at that closer, this is what our neurons are looking like. So we'll have n amount of inputs, and for each input, we'll have a weight, and we'll be multiplying those weights to each of the inputs, and then the result of all those products will be added to a bias, which will then be passed through an activation function, and we'll receive our output. Now, this output or this activation function will be kind of diving into deeper later, but for now we can look look at the other steps before that. So yeah, the first step is our inputs, which will be multiplying by weights. So we have n inputs, n weights. So there's exactly one weight mapped to each input. And then after we multiply those inputs, we'll be adding our bias. So if you look here, there's this z term. This z term is called the affine result. So it's basically before the activation function happens. So quantitatively, if you want to look at it, here's like the matrices for x and w. If you notice the one here, this is something you guys worked in the last lab as well. It's the the column for the bias term. So we will be having that again. We can use this instead of the summation to use matrix multiplication here, whichever one is simpler or easier to use is another way of representing it. So the next thing are the activation function. So the activation function, the purpose of it is to introduce nonlinearity into the system. And that might not mean much right now, but we'll kind of dive into the activation function more a bit later. So some examples of the activation function is like ReLU and sigmoid. I think you guys have seen the sigmoid function during last lab and lecture. But yeah, those are some examples of the activation function. So our output is going to be this affine function, which is got from the product and the addition of the bias. And then that will be passed through the sigmoid function, giving us our output. So some other common activation functions. There's a lot of research and a lot of math behind this, so I won't be diving into this too much right now. But just so you guys are aware of what we're kind of working with, um, a really common one that we'll be working with right now is ReLU. So as you can see in ReLU, it is linear in the positive quadrant, and then it's zeroed out for the negative quadrant. It's just useful and it's simple, so it's going to be one that we're going to be working with a lot. The leaky ReLU, as you can see, it has some kind of factor in the negative quadrant. This is so we don't lose our negative signal in case it's important. However, I'm not entirely sure with all the studies, but I do know that empirically ReLU does seem to be more efficient. I'm not entirely sure how that works, but it just is. So if you're interested in those studies, you can look more into that. So one thing that we used before is the sigmoid. So it's back again. It's there. The tan H function is similar to the sigmoid. However, one important thing you'll note is that it's centered at 0. Why this is important and how it helps the math is pretty complicated as well. So it's just something to be aware of and to know it exists. So those are some of the very common active functions that are seen. So how we actually connect each of these blocks together, the next step or like the next hierarchy after neurons is a layer. So the layer would be these guys, and then the network would be the whole thing together. Yeah, so each layer is a bunch of neurons, and we want each layer to be fully connected. This is optimal for learning. What that means is that every single neuron in the previous layer is connected to each of the each neuron in the next layer. So yeah, that is optimal for learning and what we want in our layers for them to be fully connected. So some definitions, this is the input layer. I think that's pretty self-explanatory. This is the output layer, which is also pretty self-explanatory. Everything in between, these are considered hidden layers and where a lot of like the processes happen. Just a quick revisit. If you guys remember the soft max probability, this is for classification and categorical variables. So it's the probability of the output being in a certain class rather than like a solid numerical value, quantitative. So just something to remember, and it's one of the like activation functions that we will be looking at. So next is forward propagation. So forward propagation is looking through the neural network from the input to the output. Yeah. we can go ahead. Yeah, so when you work through it in forward and make some kind of prediction, this is known as inference, and we can go ahead and give that some practice. So as you see here, we have inputs, 5 and -4, and then we have our weights. These are our weights, and then these are our biases. So this is B, this is W. So you can go in and practice doing this. I don't know if you want to take a peek at it real quick. Take like 10 seconds. All right, so if we do the first one, we'll see. So what we want to do is to multiply the weights and the inputs from the previous layer, then add the bias. So if we want to find what's at this node, what we do is we'll take 5 and 1, and then we'll take -4, and we'll take 2. As you can see, those are the ones that are connected to this layer. So if we do that, 5 times 1 plus -4 times 2, and then we also have to add the bias after. So that will give you, that gives you 1. So let's see here. It does indeed give us 1. If you want to go ahead and go through with the rest of this, rest of the layers, you'll get 0 and 1. For the next layer, as you can see, our thing is fully connected. So all 3 of these of this layer is connected to the next layer. So if we want to do this node, we see which ones are connected, and we see 1 and 1 is connected. We see 0 and 3 are connected, and then we see 1 and -1 are connected. And then, of course, our bias term. So adding that all up together, we get 1. And let's see here. It is, in fact, 1. And then you guys can go ahead and do it for the other one as well if you want to. It's -1. So those are our outputs. And just for reference, for ease of just learning, there were no activation functions in this one, but there will be in the future. So some notation to be aware of as we're working with these neural networks. The activation layer is the output of the kth node in layer L. So let's say we have like 2 layers. So this is layer 1, this is layer 2, and then this is node 1, node 2, node 3. So this is your K's, this is your L. That's just to be something to be aware of. And then the capital A represents the vertical vector of all the activations from a certain layer. So that would be like this. That would be your A2. Also, so just making sure activation output, the final one, is after the activation function, whereas the next variable, z, the affine, is the before the activation happens. And it follows the same indexing as the activation with L and K. So the next one is the weights. So the weights one is a little bit more complicated. It's a little bit easier to see in practice, but it's the weights between the previous node and the from the previous layer and the layer L from node to node. So like if you have these, let's say this is your J. Oh, sorry, this would be K. This is like the one you want. So this is J. So from this layer to this one, so this is 1, this is 2. So W2 of 3-1 or 1-3. That would kind of be how it would work. You guys can kind of see it more clearly. And then WL is the weight matrix between the layers as whole as well when it's capital. And yeah, that's just some basic notation to be aware of as we are discussing future topics. So to put that into practice as well, to look at W2 and its dimensions. So for W2, we want to be looking at, for reference, in this neural network, this node is 0, 1, 2. That's how we're going to index it. So when we're looking at W2, we're looking at the previous layer and the W2 layer. The weights in between that are as follows. So you want to go from, so how you kind of do it is you go from the first node, you list their weights, and then you do the second one, then you get their weights. So what that ends up looking like is you get 1, 2, and then you get 3, 2, and then you get -1, -1. And then for A1, since we don't actually have any activation function, it'll just be our affine. So it'll be 1, 0, 1. That's our ending result in the first layer. And the ending result, or the affine, so before the activation function, which we don't have, so it'll just be 1, -1 for Z2. So this is a summary of the results as well as the bias term from the second layer. So to put it mathematically, since following through all of these lines and all that is kind of a lot of work, to put it mathematically, this is how you would find the affine of the second layer. Yeah. So this is an important thing to remember. So this is generalized to any layer using this kind of format. And then the activation layer, of course, is just taking the sigmoid or the activation function of our Z. So now on to backpropagation.
Hey everyone, it's Holden. I'm your other Pocket Racer lead, and I'm going to be talking about the backpropagation math. It's going to be pretty fast for the amount of information that we're going to cover, so if you have any questions, feel free to reach out. So let's get our terms straight. So we have, when we're working with backprop, we have a couple different terms that we're going to talk about. So we have the number of layers denoted by L, and we have the idea of a cost function, which is just basically a loss function, but just generalized to all data points. You take the average loss across all data points, and you get the cost function. And when we work with a neuron, generally what we have is a weight and then an activation term, and then we add a bias to it. So let's say we're working with the final node in a neural network. On the final layer, we have a bunch of nodes, but in our case here, we just have one node per layer. So we have ZL, which would be the final node, and it's denoted as ZL because that's the final layer, so it's the last layer. And we'd go ZL minus 1 for the previous node. Of course, it's also going through the activation function, and you go Z2, ZL minus 2, ZL minus 3 until you get to Z0, and then that's the first node. But yeah, as you can see here, for our activation function, we're just working with a sigmoid, and for each neuron, we work with a weight term for the neuron, so that's WL. It's just the weight that we assign, and then we have our activation, AL minus 1, and then we have our bias term, which is just a constant. So for the error function that we're discussing, it's basically just the derivative of the cost function. And the cost function, like I said, is just the average of all losses for each data point in our data set. And we're going to use this error function to decide how we're going to backpropagate and update the weights in our neural network. So in our case, we are going to look for the error of the neuron before the final neuron. But the question is how? How do we do that? It's in the middle of there. It's not easy to just calculate it, but if you write out the actual, I guess the entire function that defines, the final cost function, it would become a little bit more clear. You just have to use the chain rule to figure out what the error is for any given node. So in our case, if we're looking at ZL minus 1 and we want to find uh, the derivative of the cost function with respect to ZL minus 1, we would just have to propagate that through chain rule. So we'd take the derivative with respect to ZL and then take the derivative of ZL with respect to ZL minus 1. Since there's no ZL term, or sorry, there's no ZL minus 1 term in the bias of the ZL function, we can just discard it. But then we also have to take into account the fact that there's an activation function that we're going through. So we also have to take the derivative of ZL with respect to the activation function. And then we take the derivative with respect to ZL minus 1 at the very end. And to make it look a little bit more concrete, this is what it would end up being. So you have ZL defined as WL times the activation function, and we just left out the bias term since it drops out to 0 when you take the derivative of the bias with respect to ZL minus 1. And then if we give it the activation function AL minus 1 equals the sigmoid, then we're just taking the derivative of the sigmoid when we're looking for ZL minus 1. And yeah, so if we do this and we put it all together, it just looks like this function's DC with respect to ZL times the weight for that first neuron, or last neuron, I should say, and the sigmoid function's derivative. And so that's basically how the error works. Yeah. It's just chain rule all the way down. We just continue running this sort of chain rule for each neuron before it. If we want to know DZL minus 3, then we just run the same thing, but for L minus 2 as well, and then L minus 3. Just keep doing that chain rule. It's really kind of simple. Yeah. So again, this is how it looks. But this isn't super useful yet. We've only really defined the error, which is with respect to the neuron's input values, which isn't really how we improve machine learning models. What we want to actually do is take these gradients with respect to the weights and the biases within the model, because these are our parameters that we can actually change. So in our example, let's say we want to change the first weight. That's pretty easy because or the last weight, I should say. It's pretty easy to change the last weight because you don't really have to chain rule through anything. But it is useful because you do want to change that weight whenever you have new information that tells you that there's an error, or there's a loss term that's non-zero. And you can do the same thing with the bias as well. So you take the derivative with respect to the bias, and then you can figure out how much you might want to change that bias. But like we did for the error function, we can also apply the chain rule to find the gradients for any of these other neurons within the network. And yeah, these are the um, general sort of formulas that we're working with. It's the same stuff um, as for the error functions. Basically, the same idea. But we're going to generalize this because we're not working with one node per layer. We're actually working with many nodes per layer. So we'll end up calling this the delta L. So this is just a vector that takes into account the gradient for each particular neuron in that layer, and you can denote for the ith neuron dc over dzl ith. And you can use this now to vectorize the equation. So instead of just having a single weight on dz minus 1, we can generalize this by adding in that delta vector, and we'll end up getting a whole matrix out of this. And yeah, that basically generalizes things to a vector version. And we can do the same thing with the weight with respect to L, as you can see. The sigmoid function in this case would also be a vector. It, it's yeah, it's just going to be a vector. And then the bias is also going to be an entire vector as well. Yeah, and oh yeah, we use this idea of a Hadamard product to kind of simplify the way we do the notation here. But basically, we take that linear algebra that we're doing with the weight matrix and then the delta vector, and we just multiply that new vector that comes out of that with the sigmoid vector, and then we get our list of delta. We get our delta vector for the L minus one layer.
Okie dokie, I am back. So what we're gonna discuss now is we kind of learned some of the basics of neural networks and how like we kind of work with them. So in our case, we want to be using our neural networks with images and videos to kind of understand what's going on. So we'll kind of combine our computer vision and neural network knowledge now. So before that, there's some quick issues that we need to discuss first. The said issue is what are we actually feeding into the neural network? Because we can't just like feed in the pixels because, well, that's a lot and not very important and not easy to learn from. So what we kind of want to do instead is to feed in features that are distinct and but related. And from these features, we could better learn from them. So, for example, number of legs and whether there's a tail that could lead to learning that there is a dog in the photo rather than feeding in the pixels themselves. So, we want to be feeding features into the neural network. So, how do we do this? So, yeah, rather than pixels, because those inputs are really big and not very important, what we want to do instead is to determine which pixels are related and what features they can create. And from that, from the features, we can find more useful information and less. So I hope you guys remember your 102. And I think I briefly went over this in another lecture as well. So convolution. So yeah, you take a kernel and then you multiply a matrice by it. Oh, you flip and then you multiply the matrix C and then you add them up. Um, yeah, I'm not really gonna go over it again. So quick note is that, as I said, we flip it and then we drag it, multiplying and adding everything up in that kernel. But in neural networks, for imaging, we don't actually flip it. I think it just makes it easier. I'm not exactly too sure behind the math, but we just don't do it. So yeah, so we'll be doing convolution without flipping in this case, which is called correlation. So yeah, let's start working with that. So how we look at an image is kind of like a volume. So each the image has a height and oh, hello has a height. Oh shoot, my pen needs charging. Give me a sec. Okay, we're back. So the images are kind of can be seen as kind of a volume. Um, it has dimensions of 3 by your height and width. So this would be your height and your width. And then there are 3 dimensions, each one representing a color. So, red, green, blue. So how we're going to um, filter this image and isolate features is we're going to go through each color layer one by one, and each of these color layers is called a channel. And then we'll be going and ahead and using our filters or the kernel and convolving on each of these layers separately. And since we are doing a kernel for each of the layers, we can also make a three-dimensional kernel. See here. And this three-dimensional kernel is known as our filter, which we will be multiplying our three-dimensional image. The result of this is called our feature map. Yeah, and then one thing to note is we are working with RGB, but as you know previously, one thing that we did to make it easy is we grayscale things first so that we reduce the color information, and that is something you can do as well, and that would reduce our 3D image into a 1D image, so you don't have to work with colors, but whichever one, if color is an important feature, then that is something you need to take note of. So here's just some examples of how we would do this. So this represents the 3 different layers of red, green, and blue. And then within each layer, there are different kernels, which would make up our filter. And then we would do the kernel how we would do normal convolution. We would flip and drag our kernels across said images, and then we would add up the resulting values from each of the layers, and then that will give us our final color over here. And then that gives us our output. And then we also have a bias term. One thing to note here is all the zeros on the outer edges. We'll kind of go over that later. But yeah, if you want to work through it, make sure you understand the math. Just multiply the kernel, add up everything, and then add up the results from the kernels. So each filter's goal is to look for a feature. For example, to look for this curved line, we outline it with ones in our filter, and then the rest of it we do -1 or zeros or whatever value works. And by doing that, it should highlight the the feature when we flip and drag it. We'll get how close it is to said feature. So we'll be having multiple filters. We'll have our image, we'll pass in a bunch of filters, and each filter will represent a feature that we're looking for. And by doing that, each filter will give us a feature map, and we will be able to have all of our features. So yeah, as you can see here, if the pixel is part of our feature, it will add to it, while if it's not, it'll subtract from it. And what that does is that the convolution will have a higher number when there is a feature there, and will have a low number when the feature is not there. So that is what we're trying to do. So just to go through the um, process again. So each layer will have many filters, with each filter trying to isolate a distinct feature. And then each filter will then produce a feature map, which will show that, like, whether that distinct feature was found or not. So each filter each filter will have one or more kernels to find um, the feature, and then each kernel will be for one channel, which was either RGB, so there will be 3 channels in total. And then from each channel, we'll have a bunch of feature maps, and then we can put all those together to have a 3D volume containing all the features that we were looking for. So yeah, that's just the how it looks again. So those zeros at the edge, if you notice when we were doing the convolution, the point of this is um, the pixels along the edge of the image will only be looked at when we are looking at this kernel normally. However, that's typically not enough information. So a lot of times we want it to be seen at the center. So what we do is we add zeros around the edges so that the edges also get the chance to be filtered and considered. And this is known as zero padding. And that's something important to consider. So some hyperparameters to make sure of is the step size. So how big our kernel, oh, sorry, how much the kernel is moving each time. And then the filter size, which is the size of the kernel. And then the filter count, which is how many features we're looking for. And then the zero padding, which is how much zeros we need to make sure that we cover all the edges. We don't need to pause. Yippee! All right. So we're gonna be talking about pooling. So a big thing is when we're working with images and kind of uh, neural networks is too much information. So with a model that's too complex, is we're likely to overfit it. So if our feature maps are too specific, um, we might cause overfitting. So just to ensure we know what that means, our goal is to kind of predict things when it comes to neural networks for our case. So the goal is not to copy what we see. So let's say we have some graph here. That's like kind of not the best, whatever. So, if we overfit the graph, if we make the data learn too well, which is possible for our graphs, it would kind of like, it would follow this. So when we try to predict something, it won't work well. But if we kind of do it more loosely, it will be able to like follow it. So we don't want the information to be too heavily learned on training data. We don't want it to be too specific. And this often happens when our model is too complex, when it considers every single variable, when it considers every single pixel. So we want to avoid this. One way to do this is always reducing the amount of information because you don't always need all the information. You just want to make sure you are working with what is important. So if you remember from before, the downscaling is one helpful way of reducing such information. And yeah, we can get into that. So how we did this was taking a kernel through the image and then having a step size that would reduce how many um, how many times we're dragging the kernel, which results in a smaller result. In this case, you can see that we're taking the average, which is multiplying everything in the kernel by the size of the kernel. And then we're taking the average of these four, and then that will give us our new smaller result without losing any information, important information. So as you see with that one, we were taking the average of the image to make it smaller. However, there could be some problems with this. As you can see, when you're doing like a white and black image, for example, um, all the black will gray out the white, and it becomes a little bit harder to see, and there's like less white and less to work with because that's usually our feature color. So to avoid this, um, we don't want to be making gray. So instead, we can do, rather than averaging, we can do the that's kind of arbitrary. So rather than taking the average of the each kernel step, we're going to take the maximum. So in RGB, white is 255 and black is 0. So when we're taking the maximum, we'll be prioritizing white. So if there's white in our kernel, then we will make it white. So how that looks like is this. So as you can see, um, since we are prioritizing white in our kernel, it'll be a little bit blurred and a lot more white. However, the feature is still clear. We can still kind of tell what it is, and it's easier to work with when there's less information. So we are able to maintain the size of our feature while reducing all the extra things we don't need to. So that's the basics of pooling. And then one final thing to go over. So as we mentioned, our when we're doing neural networks to learn optimally, we want things to be fully connected. And what we mean by fully connected is each previous layer in a neural network is connected to every next neuron in the next layer. And that is our goal. So considering this begs the question, what are we actually going to be passing into our neural networks? I think I briefly said it earlier, but we want to be passing in our features. So in order to do this, we're going to convert and flatten our feature maps and results to get something that we can pass into our neural network. So what we're going to do is, what we mean by flattening is we're going to convert the image features into numbers. So if the feature is present, it'll be a high number. If the feature isn't present, it won't be a high number. And we do this because, as we said, neural networks typically work better with numerical data. So we're going to do that conversion and learn from those. And then once we finish learning from all those features and trying to get our result, for example, like whether the picture is a dog or not, We'll then do our softmax probability function, and then we will discover the probability of it being such a classification. So that's pretty much it for now. I hope you guys enjoyed learning about neural networks, and I hope you guys are getting through that lab too, and look forward to lab 3. Hope to see you guys back in person. Thank you.